Hello and welcome back to differential equations section 3.2. Yeah, this is like what happened?
It wasn't that enthusiastic. Like the first thing, hello, and both no, hello.
Yeah, because we're on hell now. Just
Yes.
Enthusiastic.
It's 400 degrees over here, and yeah, we can make cookies without the oven. We are going to look at the second order differential equation with not constant coefficients but functions as coefficients, and we have to be very careful that all of these functions are differentiable everywhere. We call those functions analytic functions. If there is a point at which they are not differentiable, those points called singular points, we have the next section to address those issues. So we start with the standard thing we had in our chapter 2, right? When you had A of x, B of x, and C of x in the second order differential equation, and then we convert that, right, you dividing everywhere by ax, which is not 0. So we divide everywhere by ax and we convert that into y double prime plus p of x y prime plus q of x y equal to 0. And just make sure. Okay, good. So now we need to make sure that functions p of x and q of x are differentiable everywhere. So p of x and q of x need to be, yeah, let's use the word, so analytic, which means differentiable at all points. So if you think about equations, for instance, x y double prime plus 3x y minus x squared y equal to 0. As you divide by x everywhere, you y prime. Thank you. Y double prime plus 3y prime minus xy equal to 0. So this is analytic, meaning differentiable. If you look at the function 3 is a constant, you can differentiate that, and x is a value, you can differentiate that. If you look at the example x y double prime plus 2y prime minus, I don't know, x cubed y equals 0, when you divide everywhere by x to get y double prime alone, you get y double prime plus 2 over x y prime minus x squared y equals to 0. This is not analytic because not differentiable at x equals 0. You have that term 2 over x, and that one is not differentiable at 0 because there's the vertical asymptote there. So if we have a problem where you have the analytic, right? well, it's differentiable, we can use our power series expansion. So we are going to get maybe I should write this as a rule. So if we have y double prime plus p of xy prime plus q of xy equal to 0 is analytic at x equals a, then equation has two linearly independent solutions, each one of the form. So then we have then equation, then differential equation, there we go, as two linearly independent solutions of the form, and here's your power series, y equal sum 0 to infinity Cn x minus a to the n. Our goal is to figure out Cn, just like I did the last example, except better. No, x minus a, you remember the issues with centering the function, yes, centered at a. It's a power series. So centering at a is if you have, for instance, if you need to compute e to the 3, you can do the power series around Taylor expansion around 3 and compute, because the power series centered at 0 will give wrong answer because it's not precise enough. So what you do is you do the expansion at a. But for our problems, if the expansion is not specified that you need to go at 7 or 1/2 or whatever, you just use x to the n. So this is the general case where you use x to the n. So let's take a look at the wonderful example which should we do the one that is done in the book or do another one so you have multiple examples? Do you want to see the example from the textbook or you want the example from homework? Homework. All right, sold. Problem 10 looks sufficiently evil, but not too crazy. 3y double prime. We can do any other. Let's start here. There's more life after this. So we have this differential equation. And you could go and divide by 3 everywhere, but you don't have to. So we can drag that 3 through the problem. We start with assuming the solution of y equals summation 0 to infinity Cn x to the n. And then, yeah.
So to start off, how would you know to do power series?
The problem says use power series to solve the...
We don't have to do classification?
No, it's just power series grinds through everything. It's one of those things that shreds through any problem you can have. And because you're doing these cases at the end with n equals 0, n equals 1, n equals 2, it gives you all the coefficients, so that gives you points along which you can plot. So these problems just plow through any situation you might have.
So by leaving that 3 in, does it change? It's still a second order homogeneous?
Yes.
Is this one linear or non-linear?
It's linear. It's second order. It's homogeneous.
Constant coefficient?
It's not constant coefficient because you have x. Constant coefficients means all numbers.
All numbers.
But we have x there.
And the reason why we know that we have to use power series is because there's that x.
Yeah,
Didn't say use power series. You know to use power series.
because of x. Yeah, because, I mean, why would you use power series if the coefficients were 3, 1, and 4, right? You just use the r and you're done in hopefully a minute rather than cranking this for 35 minutes, right? So, all right. I got to get into that group, whatever it is, because it's just, yeah, we'll talk after. So y prime needs to be, the derivative of this starts at 1, goes to infinity, and we know it's n cn x to the n minus 1. And y double prime is summation 2 to infinity of n minus 1 cn and then x to the n minus 2. Now guys, this is really tricky. You don't want to shift counters yet because you don't know what's awaiting you in the differential equation until you plug everything in. Remember the one where I said you plug x inside, right? We are going to do that here. So you have to be careful about that. So now I'm substituting everything. This is going to be 3 times the second derivative. So 3 times the summation of the is 2 to infinity n minus 1 cn x to the n minus 2. And then I have plus x summation 1 to infinity n cn x to n minus 1 minus 4 summation cn x to the n equals 0. I'm happy when it fits in one row. Now, the first step is to bring x in. And you see that x n minus 1 becomes x to the n. So that's aligned, which means you can't shift the counter, because if you shift the counter, you're going to mess that one up. So this is where the decision-making starts in these problems. Do you shift the counter? Do you leave it alone? Well, we do shift the counter for the first one. We leave the counter alone on the second one. But you have to make the decision where to shift it now. So, you see, this 4 goes in, so it becomes 4 cn's, right? X to the n from 0 to infinity equal to 0. All right. Oh, what happened here? Oh, come on. Sink. There you go. It's definitely not something to say if you're on Titanic. All right. So, sinking with the cloud.
Can you just repeat that again? What did you say about not shifting it there? Why would you?
That's going to be discussion now.
Oh.
So let's do some critical thinking. All right, guys. So what I would like is for all counters to be 0 and all exponents to be n with whatever blah we have in there, right? Can I achieve that? And the answer is no. I cannot achieve that because I already have x to the n and x to the n that match with the different counters. Now that situation you can resolve by peeling off single term here. If you peel off n equals to 0, you are left with the summation 1 to infinity 4 cn x to the n. So it seems that all of these together should meet at the counter 1. They should all meet at a counter 1. This one I can shift to anything I want because it's 2 and n minus 2, so that one I can shift anywhere. Now the trick is that I'm going to work to shift this to be x to the n. As I make that x to the n, this will go to 0, so I'll have to peel one term from there as well, and then it will be 1 across the board. If you haven't picked up what I said, it should be hopefully clear as I start working on this. I will repeat this one more time. The major goal is to have all of them to be x to the n. That's the target. Because the counters can all agree if you peel off a term. Let me just give you an example of that. If I have, I will erase this because we are mid-problem. If I have a summation of, let's say, Cn x to the n, and the counter started at 1 to infinity, and I have to add to that summation dn x to the n, but this is 0 to infinity. What I can do is, since these guys are already on the same, shifting the counter here to 0 will change the exponent, and it would make it incompatible with this one. I have to have the same exponent. So instead of me changing the counter, because that would mess this up, I can peel off one term from here. Now, what does it mean, peel off one term? That means compute the 0th term, and then your series will start at 1. So copy the first series as is, which is Cn x to the n, plus, and now compute the 0th term. 0th term is d0 times x to the 0, and then you have the rest of the series, which starts at 1. Now d0 x to the 0 is just d0, which is a constant. But now if you look at the series, they start at the same counter, and they have the same exponent. So now I can call this d0 plus summation 1 to infinity, and I can get the recurrence equation here, and x to the n, which was common. So when we shift the counters, we have to shift them so that x to the n matches throughout. And then deal with the fallout with the counters. If we can't fix all the counters to work off of the bat, then peeling is the option for us to deal with the situation. So now, when what I have to do is I have to peel one term there. Now I see that I have to shift the counter by 2 over here to get this to x to the n, but when I do that, this one will go to 0, so I'll have to peel 1 there to get to 1. All right, so shift the counter. When I shift the counter here, it will be 0 to infinity, 3n plus 2, n plus 1, cn plus 2, x to the n. You will say, well, really? I said, yep, I shift the counter just like that. And if you don't believe me, you will go and you will say n equals 2 minus 2 minus 2 on both sides. K is n minus 2, so n is k plus 2. And then this one becomes plus 2, this one becomes plus 1. And right, you will do the shifting when you study this. Plus summation 1 to infinity n cn x to the n minus summation 0 to infinity 4 cn x to the n equal to 0. Great, they all have x to the n, but they don't start at 0. We are stuck with this term that starts at 1. So we must peel off terms on the first and the last. To peel off the term on the first one, you plug in n equals to 0. So peel off n equals 0, peel off n equals 0. So with n equals 0 over here, I have 3 times 2 times 1 C2, right, because n is equal to 0, and then plus the remainder is 1 to infinity 3 n plus 2 n plus 1, Cn plus 2, x to the n. So we achieved the start at 1. Plus, this one we don't have to do anything because it already has two features that we need, which is counter is at 1 and it's xn. And finally, minus, we have to peel off a term. So peel off n equals to 1, we get 4c0, and then minus the rest of the series. Now it starts at 1. Now we combine this into 6c2 minus 4c0. That's the constants, pushed all of those to the front. Plus, and now combine all of the sums because they all have counter at 1 and xn. So what we have is 3n plus 2, n plus 1, cn plus 2, plus ncn minus 4cn, all of that, x to the n equal to 0. And there's your recurrence equation. So now what I need you to understand, guys, is that this puppy over here is n equal to 0 term. The rest over here start at n equals to 1. That should be clear from the power series. But let me just outline that just in case. So your recurrence equation now is 3 n plus 2, n plus 1, cn plus 2, plus, and I can combine this cn as n minus 4, cn equal to 0, right? If I factor cn in the last two terms over there. So there's your recurrence equation. I'm going to box this blue. Actually, do I want to box this blue or I want to solve this for Cn plus 2, huh? Cn plus 2 is equal to negative n minus 4, right? You shift this term to the other side. So I'm going to call it 4 minus n Cn, so I don't have negative signs. And then we have 3 n plus 2, n plus 1. There we go. This is the recurrence relation. Again, when I move the term n minus 4 Cn to the right, it becomes negative n minus 4. And then I swap the order of n and a 4, and that kills the negative. So it's 4 minus n Cn divided by all of this mess. And what happens now is terms. So we already have our n0 term. For n equals 0, we know that we are getting 6c2 minus 4c0 is equal to 0, from where we have that the c2 is equal to 4c0 over 6, which is 2c0 over 3. So that's our n equals 0. For all others, we refer to the formula. So what is n equals to 1? N equals to 1, we get c3 is equal to, and now we compute, 3c1 divided by, plug in 1 everywhere, so that's 3 times 3 is 9 times 2 is 18. So we have 3c1 over 18, so that's c1 over 6, right? So c3 is c1 over 6. N equals to 2. It's just messy. N equals to 2. Again, plug into the blue box up there. So n equals 2. All n's get replaced by 2. We get 2c2 divided by That's a 4, that's a 3, it's a 9, it's 36. So it's 1 over 18, so C2 over 18. But we know that the C2 is C0 over 3. So C2 is 2C0 over 3 and everything over 18. So that's 9, that's 27, right? So C4 is C0 over 27. C0, 2 cuts 18 into 9, 9 times 3 is 27. Bueno. N equals to 3. That's a C5. C5, so that's N. So we have just a Cn, so that's C3 divided by, when you plug in 3, you get 3 times 5 times 4, 60, yeah. Yeah, it's a half of 5 factorial.
Half of 5.
Yeah, 4 times 5, 3 times 4 times 5 is only missing a 2 for 5 factorial. 5 factorial is 120, so 120 divided by 2 is 60. So C3, that's a C1 over 6 divided by 60. This is C1 over 360. So C5 is C1 over 360. Guys, the pattern is slowly emerging. Slowly. You have 2 separate strain of values. Observe that all of the even ones will be in terms of C0, all of the odd ones will be in terms of C1. Therefore, you are creating 2 power series, one that will be C0 times a power series, and the other one will be C1 times a power series. And they are added together in a superposition to get the overall solution. So let's compute 2 more, because we can, and we'll leave it there. N equals to 4 gives me C6. Now that becomes negative, no, that's 0. Boom. That one is 0. Do we see that? What's 4 minus 4?
0.
Done. Oh, you like that term. N5 is C7. What's C7? So that's negative 1 Cn. So negative C5 divided by, now we have 6 factorial, that's 720 divided by 360. You okay? And then that gives us negative C1, right? C5 is C1 over 360, so negative C1 over 360 over 360. So this is negative C1 over 360 squared.
Wait, is, if we're putting 5, it would be 3 times 7 times 6.
3 times 7? Oh, it's not 360. Yeah, it's plus 2. All right, so it's not 360. 360 would be for C6. Yeah. What do we have? We have 5, so we have 6 times 7 times 3.
42 times 3?
Is that 42 times 3?
Yeah.
What did I say? We have 3 times 7 times 6, right?
Yeah.
It's a 42 times 3. That's 126. Good. So that's 126. No, 126 over here. So this is 360 times 126. And it's negative on top, yeah. Great. All right, so what's the solution now? Solution is y equals, and now we have all of these C0 terms, right? So the first, we are going to get a power series now. So first term is n to the 0, and we have a C0 there. So I have to do C0 times everything that goes to C0 plus C1 times everything that goes with C1. So for n equals to 0, oh, and we are remembering that y was given as this. So C0 on the first one, what does C0 have? Oh, C0 has nothing, it's just the first term is the first term. So x. No, 1. Because x to the 0 is 1. Plus, the next time C0 appears is in n equals to 2. And we have C0 over 27, so it's 1 over 27, right? Because we factored out C0. And it's x squared. Because it was n equals to 2. Plus, the next time C0 shows up is in this term number 4, which is 0. Plus, and it will go forever on those. Now we go for C1s. C1 shows up for the first time for n equals 1, and it's C1 over 6. We are factoring out C1. No, sorry. First time C1 shows up as a C1. So that's just going to be x, right? Because C1 times x to the first power. Then the next time it shows up is when n is equal to... No, it's a 1/6 times x. What am I talking about? 1 over 6 times x. There we go. Plus, the next time it shows up is over 360, right? So 1 over 360, and that was n equals to 3. The next time is a minus 1 over whatever this monstrosity is. X to the 5 plus ... forever. Now, sometimes it's easy for us to recognize the patterns here and call them sine, cosine, hyperbolic, or e or something. In this case, nope. So what do you do with this? Well, if you have initial condition, you calculate C0 and C1, right? Because you just take derivative and come on, it's all polynomials. So you take derivative, you plug in initial condition, you get C0, C1, and then you have your and then you have the polynomial. You can graph the polynomial and see it because it's you're done at that point. Right. So this is the general solution, and that's it. Two-thirds C0. Oh, yeah, you're right. 2/3 is right here. Thank you. Thank you. 2/3, guys, not 1. 2/3 on C0. Because the 2/3. on the first term, n equals 0. It's 2/3 times C0. Very good catch. Thank you. That means you're understanding this so far. Well, generally, you know, up to n equals 5 should be okay for you to, because n equals 5 is 6 terms, and if you have 2, right, it gives you the first 3 terms of each of the series, and usually 3 terms is all we write when we learn e to the x and sine x and hyperbolic and so on. So you should be able to recognize if it's a basic function right away. Now, what I'm highly recommending is for you guys to, once you get home, right, to study this, do the equation that you know. Do equation that you know, because in the pattern you must obtain sine and cosine. And that equation is y double prime plus y equals 0. So here, I'll write it in block. Do this at home. Y double prime plus y equals 0. This one has to come out as the power series for sine and a cosine, because that's the solution for this. It's a sine and cosine. C1 cosine x plus C or C0 or whatever it is. So this would be like your first order of business to do that, because that one gives you, you know what the answer is supposed to be, and you do the whole thing, and then you keep figuring out what are you missing, what is the issue, what is the problem, what is wrong, as you are going towards this. I want to work on one more. I understand we have 11 minutes left, well, 10 and a half minutes left. So if I
Can you go on and show with the
talk sufficiently fast,
or no, I was going to say if you can show with that program, or no, can you do that on another time?
what program?
Yeah.
Oh, in Mathematica you just say solve.
Oh, and just plug that in and
You say try first solve, and you put these brackets and you just write the entire equation in here like that.
Oh no, I thought the one you were going to give us. I thought this one.
And if that doesn't give you the answer that you are looking for, you just put the word ODE, solve ODE, and then do the same thing. And that's Mathematica will solve. And since you have the full, it should show the steps and stuff. All right, guys. Now let's take a look at one of these that look a bit different, which is, let's say, problem number 6. It says x squared minus 1, leave the bucket alone, minus 6xy prime plus 12y equals to 0. Now, we start again with the same deal where we assume that the solution is the power series 0 to infinity cn x to the n. We find the first derivative, which will be shifted by 1, which is n cn x to the n minus 1. And we find the second derivative, y double prime, which is 2 to infinity n minus 1 n cn x to the n minus 2. Now, something beautiful is happening over here. We have x squared, which will offset that power. We have x, which will offset the other power. So it looks like that a lot of stars are going to align nicely here, right? Perfect. We will restart the problem. I know.
What?
Yes, this was the iPad, I would break it, but it's not, so it's precious. This is serious technology. So now, as I'm substituting everything, we have x minus 2 times 1 with a summation of n minus 1 n cn xn minus 2 minus 6x summation 1 to infinity n cn x to the n minus 1, and finally plus 12 summation 0 to infinity cn x to the n equals to 2. Right? Aren't you glad you got up this morning? Now you distribute x squared minus 1 into the first one. See, the x squared is going to knock off, but the second one, you have 4 series here, guys. There are 4 series because this one distributes and then 1 distributes as well. So there are 4 series to worry about. But 3 out of 4, you don't have to touch them. Just peel off terms. The only one that it has, there's going to be the one that for minus 1.
Question. When you say distribute that x squared minus 1 to where?
To power series.
Oh, to that.
Yeah. So, when I distribute x squared, the power series goes 2 to infinity, n minus 1 times n cn x to the n. But now, when I distribute minus 1, it goes minus 2 to infinity, and this is the only problem term that we have because it leaves us with n minus 2 power. Such is life. And then when x goes inside, this becomes minus series. Will this fit? 6 n cn x to, oh yeah, n 1 to infinity, and then plus, kick 12 inside, 12 cn x to the n equal to 0. So we need to shift only on the n minus 2. The rest is all aligned, but I have to peel terms off. Right? I have to peel the 2 terms over there. No, I actually... Oh, no, yeah. Okay, good. So, peel 2... Me. There we go, yes. All right, the voice is back. Yeah. Peel the 2 terms. Yeah, I need to reset the voice. I'm just too excited. This section is, I love it. All right. So, from the first series, we are peeling off 0 and 1. Oh no. No, we are leaving at 2. This one and this one are peeling terms. There we go. So we are copying the first series. No, Cn. Now, this one is the one that shifts. It will shift to 0 to infinity and plus 2, so that will be n plus 2 n plus 1 Cn plus 2 x to the n minus summation 6n cn xn will run to infinity and plus summation 0 to infinity 12 cn xn equals 0. Now
You shifted the count on the second?
I shifted the counter on the second because I needed x to the n.
Yeah.
The rest have x to the n, so I can't touch those. Now we peel, but we peel only on, well, we peel on these 3 because we have to go all the way to the second, right? Yes? Where does it end? When the problem is over, if that's the question. So leave this one alone, n minus 1 to the n cn x to the n, it's beautiful, minus, now we have to peel 0th term and the first term. When I plug in 0, I get 2 times 1, so 2c2, x to the 0 is, yes, and then minus, when I plug 1 everywhere, I get 3 times 2 is 6c3 x, and then the rest is starting at now I can't fit over here, minus summation 2 to infinity n plus 2, n plus 1, cn plus 2, x to the n. Bueno. Now, you.
What did you peel off from which chunk?
From this chunk, this. We peeled off 0 and 1. Because now we need counters to all meet at 2.
You say 0 and 1?
Yes. From the next chunk, we are only peeling 1, and it will put us at 2 immediately. So when I peel 1, I get 6 times 1 is 6c1. And then the rest starts at 2. And in the last one, I have to peel 2 terms again. So peeling 0, so that's 12c0. Ooh, this needs x over here. C1x.
Yeah,
12c0 plus 12. No, yes. C1x plus summation 2 infinity 12 cn x to the n equals 0. There it is. We peeled off everything we're supposed to. Please tell me this. What do you mean go with it? It's correct. What do I do from here? Oh, from here is easy. This is the most annoying parts to get up to this point. From now on, you have all of the terms that you peeled off, you put those on a pile, and you have all of the summations now condensed into a single summation. So we have, exactly. So look what we have. We have 12c0 plus 12c1x minus 6c1x, see, those will combine, minus 2c2 minus 6c3x. So these are all terms that we peeled off. And now, plus the single summation that goes from 2 to infinity, and in here goes all of the stuff that we have, x to the n at the end. So what do we have here? From the first series, right, that's the first series, we have n minus 1, n cn. X to the n is outside. The next one is minus n plus 2, n plus 1, cn plus 2. Next one is 6n cn. Oh, it can't fit. And over here, plus 12 cn. Yeah, so, well, we have, let's do just a little bit more work over here. We have 12c0. Now these guys combine into a 6c1x, so plus 6c1x, minus 2c2 minus 6c3x, plus summation 2 to infinity. Now guys, observe that the plus 12 over here, which is a cn term, and then there is this cn term, and then this cn term. So there are 3 cn terms that we can smoosh together, right? So from the first term, I have n squared minus n. From this one, I have minus 6n, and from the last one, I have plus 12. All of these, cn, minus n plus 2, n plus 1, Cn plus 2 close x to the n equals 0. So now these guys combine, and we can't, I mean, minus n minus 6n is minus 7n. Yes?
Scroll, like,
I can.
Bit more. Touch more. Like that.
So what is the recursion? Recursion equation is, dare I say clearly, Cn plus 2 is equal to, right, n squared minus 7n plus 12 Cn divided by n plus 2 n plus 1. That's our blue equation. All this work to get the blue equation. Now you crank n equals 0. Well, n equals 0 is already done. Yes?
You always solve for C at n plus 2?
You always solve for the biggest one, yeah. The largest one, yes. So it's either, you have to have Cn, Cn plus 1, Cn plus 2, Cn plus 3, Cn plus 4, you'll solve for the largest one. Oh, we're gonna go till 8. I heard why.
Yeah, what?
In a recursion equation, right, you want to express the new one in the terms of the old one.
Oh, yeah.
You create a new term by using up the old term. You are supposed to have this one, and you build the next one. That's the recursion. That's why. So n equals to 0, guys. That gives us C2. And the C2 is, when we plug 0, is 12 C0s divided by 2, which is 6 C0. For n equals to 1, it's a C3. And the C3 is going to be, now we have 13 minus 7, that's a 6 divided by 6. Ooh. Is it true? 13 minus 7 is 6. 3 times 2 is 6. 6 divided by 6, yeah. Nice. N equals to 2. That's going to give us C4. C4, 4, 14, that's a negative 2, so it's a 2C2 divided by 4 times 2 is 6. C2 over 3.
You said 4 times 2 is 6?
4, oh, is that 4 times 3? 4 times 3 is 12. Sheesh.
I have a question. Where did the peeled off terms go? Because like before I thought you said when n equals 0, you said those peeled terms. And then put all of those recursions.
They go in front of the equation. We have x's as well.
Okay.
You get actually
They get attached to x to the n, yes. C5. Yeah, obviously, right? 9 minus 21 plus 12, 9 and 21. Is that a 0? Oh, yes. 6C0 over 6 is C0. Okay. Guys, is this 0 again? 3 squared is 9, 9 plus 12 is 21, 21 minus 21. Nice. And then this is gonna go forever. Then you write your solution, you go back, pick up all of the terms that you peeled off, you combine x's with x's, replace C2 and C3 with C1 and C0.
Professor, how?
right? I needed like a bar to get it. I was freaking out. I got flu. I was sick of shit. I think the water heater went bad.
Welcome to differential equations.
I'm like,